Health Portal. And our February 6th Tech Talk is will have Dr. Gary Henry from University of Delaware. So do not miss also our next month's Tech Talk. So again, I'm really delighted to introduce our good friend, Dr. Tim Bunnell from Nemours. Tim has multiple titles. He's a director of the Center for Pediatric Auditory and Speech Sciences at Nemours Bioinformatics Core. He's also the head of the Speech Research Lab within the core. He's also the director of the Nemours Biomedical Research Informatics Center, or BRIC. And BRIC maintains the computing infrastructure for Nemours Biomedical Research. He's the co-PI and informatics leads for PEDSnet, and I think that's what you'll be describing for us. And he's also adjunct professor in the Department of Computer and Information Science at University of Delaware. Tim Bunnell obtained his PhD in experimental psychology from Penn State, concentrating in human speech perception and acoustic properties of speech. He's currently PI on a large NSF grant related to voice banking, and is co-investigators on multiple federal grants, including INBRI, PEDSnet, and multiple others. And he has also multiple publications. So we are absolutely delighted to have Tim for our first Tech Talk of the year.
Thank you very much, Claudine, for the introduction and for inviting me to present here. I'm going to need to stand in the room a ways so that I can actually see what the slides are. I don't have this talk memorized. I was making it up as I went along pretty much. And part of the reason for that is that what I'm presenting is actually work in progress at Nemours right now, or at least the second part of what I'm doing. We've had PEDSnet, which I'll talk about in a moment, at Nemours for going on 5 years now. And we're starting to now see how can we integrate the information that's available in the local Nemours PEDSnet to really inform our own patient care. So that's kind of what I'm going to be talking about today. Oops.
I'm sorry, I'm just trying to get it full for you. Yeah, that's good. Thank you.
Okay. Nothing to disclose. So basically, the discussion is going to break down into two areas. For starters, I'm going to tell you a little bit more about PEDSnet and the OMOP data model that PEDSnet is based on. I believe some of you here in the Value Institute are familiar with the OMOP model. For those who aren't, I'll go into some of the features of the model and the design of the model. And then the last part of the talk, I'll show you a couple of the things that we're just starting to bring online related to using the data in the OMOP PEDSnet common data model that's just Nemours data to inform our own patient care. And what we are doing with that is trying to bring in a specific set of disease states that we want to map the course of or look for adverse events in. The PEDSnet network was founded by these 8 institutions. Since its founding, the Boston Children's Center has stepped down. We're actually in the process of adding several more, perhaps as many as 6 additional pediatric institutions around the country to the network. But right now we're technically a network of 7 rather than 8 sites, with the Children's Hospital of Philadelphia, CHOP, as the prime site and data coordinating center for the network. The PEDSnet network is one of the CDRNs in PCORnet. So PEDSnet was actually funded by PCORI to set up one of their clinical research data networks, and that's what PEDSnet is. Just to give you an idea of the amount of patient coverage in the overall PEDSnet data set right now, there's about 6.5 million distinct patients in the overall network data, and they cover the U.S. in this manner. You can tell that that we have the East Coast especially well covered. We're looking to see if we can get a little bit better coverage out west and in the south as well. Now, the PEDSnet Common Data Model, which is built on top of and in a customization of the classical OMOP Common Data Model, has these as the sort of primary fact tables. So there's really just these 6 tables that you need to really understand in order to be able to know where to find the facts. The people table lists all of the possible people in the database. As I said, for the national network, that's about 6.5 million kids. For Nemours, that's a little over 2 million patients. So we've got a pretty sizable just internal data set as well that we're working with. There are also every possible encounter, with the electronic health records that we have for each patient is recorded in an encounters table. And then the 4 primary fact or concept tables below that comprise conditions or diagnoses, lab results and measurements. So not only do we have lab results there, but we have height, weight, BMI, and things like that in the measurements table. Medications, also called drug exposure table in OMOP, and procedures, which are things like surgical procedures, x-rays, imaging, and that sort of stuff. Well, imaging sometimes turns up under lab results and sometimes under procedures, so it's a little bit strange that way. Drilling down into the model a little bit more, for PEDSnet, we have used the full standard clinical data. So all of the tables that are actually listed there, the 6 that I showed you before, plus several others that are smaller or less interesting subsets, are part of the PEDSnet model. We are not using any of the standardized health economics. There's no economic data in the current PEDSnet data model at all. But we are looking at the standard device derived elements, and the standardized health system data. So we do have location, care site, and provider information in the system as well. And over here on the right are a set of standardized vocabularies and concepts that are basically they ship with the OMOP data model. They're not part of our data, but they're what allows us to describe everything that's in our data in the common data model. And just drilling down into that a little bit more, central to the vocabulary is a concepts table that lists all of the possible concepts, all the reference you can use for any fact that you want to identify in your electronic health records. And those concepts are then supported by things like concept relationships table that allows you to ask, does this particular concept map to this other concept in a different vocabulary? And the concept ancestor table that allows you to look at hierarchical relationships among the concepts so that it's possible to look at what's the parent concept of this concept and what are the children concepts of this concept. So just as an example of that hierarchical relationship, which is really a useful feature, technically the vocabulary for conditions in PEDSnet is the SNOMED nomenclature, but each of the SNOMED codes is actually mapped to a specific concept ID. And if you take a high order concept ID, like the one for otitis media, which is this long integer here, you can take that concept and you can say, okay, I want to find that concept and all of the descendants of that concept. And a simple query like this that has only one concept specified in it can then query the database and pull out all of the instances of anything that's related to otitis media. So you don't just get the fundamental otitis media, but you get chronic anticoagulatory suppurative otitis media, acute allergic mucoid otitis media, and so forth. I didn't list all of them. There's actually quite a few more that would come out of that single query. So as a way of querying the database without having to develop large lists of individual concepts that you need to query. This is a very powerful technique, and it's one that we use all of the time in our searches. Just a brief glimpse of how we get from our internal Clarity database, which is the Nemours electronic health record system, to the OMOP model. There's about 12,000 tables in our data warehouse that support the Clarity model, and 125,000 fields of data. So the people who are in charge of the data warehouse tell me that when they bring someone new into the system, it can take them up to 4 years to become really familiar with this data model and be able to do interesting and complicated things with that data model. But what we do then is grind that through a fairly complicated ETL process where we extract, translate, and then load the data that we've pulled from the Clarity data model into a Postgres database that's organized along the OMOP common data model format. And on the other end, we end up with, instead of 12,000 tables, just 18, and a total of 575 million records in that database. So it's still a pretty substantial database, but it's now in a format that, because the common data model is so concise, that someone can learn in months rather than years when you bring a new person into the system. So that's a significant advantage of that sort of data model. Just sort of by comparison then between the sort of classic, in our case, EPIC electronic health record system and something like PEDSnet that represents the same data, what you can see is that there's a lot of these discrete elements that are in PEDSnet that make it easy to learn the data. It's all normalized and shareable so that different institutions have the same set of concepts, so that a particular concept like that otitis media concept is presumably the same thing in all of the institutions who participate in the network. The data set is a limited data set. We've obscured all of the patient medical record numbers and things like that. The only identifiers in the fundamental data model are zip codes and actual dates. And when we export the data to be analyzed by someone, we typically skew the dates and limit the zip codes to 3 digits unless someone has a good justification and IRB approval to get the PHI data out of PEDSnet as well. On the EPIC Clarity side, it's not easily learned. Obviously, even though 2 different hospitals may have an EPIC system, it turns out that there are so many decisions about how things are coded in the system that you can't take data from Hospital 1's EPIC and necessarily be able to compare it unambiguously with data from Institutions 2's Clarity system. Both systems, of course, have the discrete elements. What PEDSnet lacks are these things that we might call the indiscrete elements. They're the ones that could potentially expose PHI, such as free-form text fields. EPIC has a very useful feature called smart forms that we're not trying to transfer because right now every institution has their own smart forms that they've developed, and so there's no standard to translate those into. But clearly those 2 data sets are designed for different purposes, and in PEDSnet being the one that's more research friendly, Clarity being the one that's really needed when you go in to bill somebody for their medical care. At Nemours, what we've done is taken the PEDSnet data set and actually put a web-based interface in front of it, which unfortunately you can only get to if you're in Nemours and have a Nemours login, or maybe that's fortunate, I'm not sure. But we're letting people get access to the PEDSnet data set so that anyone in Nemours can use some of these tools like Atlas that I'll talk about in a minute, or they can go to a form that allows them to request a data extract from the PEDSnet internal Nemours PEDSnet data set now, not the national network. for future analysis. This slide in PowerPoint was really clever because it has these little pictures that pop up one after another, so I can talk about it. It's an illustration of the ATLAS tool, which is an open source package that is web-based and designed to run against the OMOP standard data model. This is basically an unmodified version of ATLAS that we're able to run at Nemours that connects directly to the PEDSnet version of OMOP in Nemours. So it's a pretty versatile and transferable piece of software that allows people who don't have coding skills, who are not, facile with SQL and other languages, to still be able to get into the system and explore the relationships between data elements and pull out patient cohorts to define a cohort that they might want to work with. This illustration was talking about epilepsy and the idea that you could go into ATLAS and first define some concepts like, what do I mean by epilepsy? And you find the concepts that are to be queried to define the term epilepsy. And then you could ask, what do I mean by an EEG evaluation? And you can find some codes to represent that. And so you can define different concepts like that are higher order concepts. And then you can define a cohort by combining the higher order concepts into a single cohort, such as patients with otitis media who have had, epilepsy, patients with epilepsy who have had at least 3 visits with our system, who have had at least one EEG study, so that we were sure that people were concerned about that and that a diagnosis was well-founded. People who don't have a developmental delay or autism, because we wanted to eliminate some of the patients. So you can take all of those different concepts and apply them to define a single cohort of people that you want to do research on. And then with ATLAS, you can actually print out a file that either gives you just a raw list of what are the concepts you need to pull out of the database to get this cohort of patients, or it gives you a JSON file that you can apply to some other software, and there are tools that come with the ATLAS Odyssey suite of tools that allow you to take the output of ATLAS, dump it right into another program, and then run analytics studies, predictive analytics, and so forth on that. We chose not to exactly go that way, but rather to try and then roll some of our own analyses based on the output of this. So ATLAS then lets you do everything up to the point of having defined a cohort. But once you've got that cohort defined, ATLAS doesn't provide any of the specific tools that you need to do the analysis. And that's what some of the other tools from Odyssey are the ones that we're working on at Nemours, specific to the Nemours data, would allow us to do. And so here's where I'll sort of stop talking about PEDSnet per se and start to talk a little bit about the work that we're trying to do with disease course mapping and predictive analytics. Our VP in charge of patient quality control and patient safety and things like that in Nemours was sort of pressing us to see what we could do with the PEDSnet data set, the Nemours, again, data for PEDSnet, to work to improve patient care at Nemours. And we started doing that by identifying several disease states that are important to us. They included things like epilepsy, obesity, asthma, blocking on what the others are at the moment, but that's all right. Anyway, we came up with between 10 and 12 different disease states that we wanted to look at, and we've started sort of going through them one at a time and pulling out information about that disease state and looking at how we can characterize it. And we've developed tools. We're working primarily with R and RStudio and the Tidyverse tools. Those of you who are not familiar with those should become familiar with them. They're really, really useful for doing the kind of work that we're doing here. So let's take a look at how the analysis for a disease state progresses a little bit. We start, of course, with a definition of the cohort, which is nothing more than a list of the patient IDs who are a member of that cohort, a start and stop date for the data that we're interested in. And those are not literally stop and start dates, but they're anchors. You may want to use the event 1 date as the event where something occurred, and you might want to also have 1 year of data up to that event, and then all the events from event 1 to event N, and potentially you might want to have some amount of data after that event. But these two are typically marked by some significant event in the patient's care pattern that you want to center your analysis on. We typically also record the number of events here so that it's easy to say, well, I only want patients who've had at least 5 of these events in their system. And then the data tools are agnostic as to what other columns one might choose to put in the cohort file for analysis. But once we've identified the patients in the cohort, the extraction scripts then run through here, and for every patient they extract every encounter with that patient and all of the data related to condition occurrences or drug exposures or measurements in labs or procedure occurrences for that patient. So the data grows very, very rapidly when we start extracting it. And we extract into a long form, such as on the left here, where for each person, we have data for each visit, and within each visit, we have data for every one of those types of facts that we might want to record about the patient. And that's a very useful form of data if you want to do longitudinal time course sorts of studies. But for a lot of predictive analytics, it's not very helpful, because what you really need is something more like this, where you have one or maybe a small number of rows per patient, and all of the elements in every row are exactly the same. And so we have procedures for converting from this format to this format, where we have persons and features arrayed in wide form. But the other thing that's really important, and probably I'm preaching to the choir in this room, for any extraction of data from electronic health records, even if it's been through all of the cranks that we throw it through to get into PEDSnet, you still have a massive amount of data cleaning that you need to do before you really want to dive into your data and do anything with it. So we drop patients with improbable birth dates, and we try not to have things happen before birth or after death for most of the patients in our data sets. Events that occur far into the future are probably not ones we're interested in our data analysis. There's a list then of the different types of data cleaning processes that we've now largely automated, so that from the time that we get that table of cohort members, it's literally just run a script to get from there through this cleaning phase and on to the point where we can start to do some analysis of the data. This analysis that I'm going to describe here we'll just be talking about epilepsy patients for today. And our definition of epilepsy patients, I think I already gave you the rundown here, basically. It resulted from our set of patients where we require at least 3 years of history in the medical record system, where we're sure that we saw the person before the first data, sometime by or after the last date. We found 1,670 patients, and when we extracted them in that long form, we got about just under 2 million fact records that we then want to use. And if we were to convert raw from that long form to the wide form that I showed you, we'd end up with 14,000 columns of data in the in the data table, which sometimes is what we do, in fact, although there's good ways for reducing the difficulty of the data somewhat, quite a lot. So then, after we've extracted the data, we're providing tools that let people very quickly look at some information about the demographics. There are simple functions that you can call that first extracts the demographic information and then plots the race and plots the age at V1 and so forth. We can see that for these epilepsy patients, males tend to show up a little bit earlier than females. This does not quite reach significance in a t-test, but it's pretty close. And we can look at our overall cohort for any period of time within the analysis window. How many active patients do we have? If we were looking at something that we needed a lot of active patients, we'd restrict our analysis window to something in this area, or other things we might use the entire time course of patient distribution. And the other thing, we stole a tool from text processing that worked better than I expected it to with electronic health records. And that's the term frequency inverse document frequency approach, where in this case, we take all of the patients in the entire Nemours database and we treat them as a document. And all of the terms for all of the patients, every patient in that document who has a particular concept, whether it's a condition occurrence or a drug exposure or whatever, we count all of those concepts as the words that text, that patient is exposed to. And we then combine all of the patients as members of a document and calculate the inverse log frequency of that population. And then when we extract an individual cohort, we can look at the same properties, the term frequency, the frequency of each concept within that group of patients, within the cohorts group, and compare those to the overall data set for all of Nemours and see how does this cohort differ from our population baseline of patients. And when we do something like that, for instance, with the epilepsy patients and ask what are the 10 most important features that distinguish our epilepsy cohort from the population at large, we find that, well, gosh, seizure, epilepsy, forms of seizure, forms of epilepsy, electroencephalography are all terms at the very top of the list. These are the things that set this cohort apart from our population at large. And similarly, when you look at their drugs, the things that pop to the very top of the drugs, maybe even there's an excuse for vitamin B6, I'm not sure because I don't really know anything about epilepsy. But most of the things here as well flow to the top of the chart, so that we're able to find what are the things that distinguish our cohort in each of these concept domains that we're interested in. I'll mention also there's multiple ways that you can specify a drug. You can talk about Bayer aspirin 325 milligrams, or you can talk about aspirin tablet 320 milligrams, or you can talk about oral doses, route, the dose size, and so forth. We prefer to try and roll things up to a clinical data form that lets us drop the brand and drop the dose, at least in terms of is it a 325 or a 80 milligram tablet, so that we get just the base drug. And that reduces the number of different drugs that we have to deal with. And it also gives us, usually this is really what you want to know. Was the kid given lorazepam or not? You don't necessarily need to know how many milligrams were delivered to the patient or what brand, if it was a branded drug. So these are what we were able to pull out using the TF-IDF approach to the patients. And then in the case of epilepsy patients, one of the things that we noticed is that there's a fairly high frequency of emergency department visits from these kids, and it's in part because they go into seizure and need to be brought into the emergency room rapidly. So when we looked, we just picked arbitrarily 2014 to 15 and looked over that 2 years, what's the accumulation rate of ED visits among the cohort of patients who are active in that time frame. And it gets up to around 23, I believe it was, percent of the patients by the end of a 2-year period have made it into the emergency room at least once. And you can tell from the shape of the curve here that starts out steeper and ends up more shallow, that we've got some kids who are more frequent visitors to the emergency room than others. And that same concept is shown here in a histogram of the frequency of visits, where we can see that there are a large number of children who have 0 or few visits, and there's a small number of children who have many, many visits. So again, nothing particularly surprising about that, but it's a nice way to illustrate that to people. To then make better sense of the ED visits, one of the things you can do is sort of randomly sample a 1-year interval from this multi-year data set that you've got and look at how many ED visits did you observe in that year. And by doing that multiple times, you can then begin to get some error bars around the likelihood of an ED visit in this cohort of patients. And so, in fact, we find that in the long term, about 15% of the patients are likely to have an emergency room visit within any given year. And we've got some fairly narrow error bars around that mean as well. We can also look at then accumulating over all of the patients and all of the years, the 1-year visit rate. Here you're going to hit a top of 1 because we're only talking about patients who actually had an emergency room visit. And again, we can see that the curve is negatively accelerated. And in fact, the less than 20% of the data are going to account for, of the patients are going to account for about 50% of the ED visits. So we've got a population of kids who are coming often and a lot of kids who are coming. So then we might want to start looking at what can we do in terms of our medical record information that can predict who's going to be visiting and how often. And to do this first analysis that I'm going to describe, what we did was we took all of the data and we eliminated from it all of the data that was obtained during an emergency room visit. So we're only looking at well care or care in the hospital or care in some situation other than the emergency room. And started looking at how can we predict the frequency of emergency room visits. So this is a regression analysis. How can we predict frequency of emergency room visits in this cohort of patients given the data from non-emergency room visits? And how many people are familiar with random forests? And I don't need to describe it. So I'll half describe it because about half the room. It's a way of it's called an ensemble analysis technique because it allows you to repeatedly examine a data set with a specific type of analysis. In the case of a random forest, it's a regression and classification tree analysis. So you can take this regression tree and do it 500 times, and then you have a forest. And from the forest, we're able to then do a much better job of predicting real behavior than from any given individual tree. In fact, in this case, we grew a forest of about 1,500 trees, looking at just 5 variables at a time. And I'm sorry, I forgot to list what the variables are in this case, but we'll get close to that in a minute. And we're able to account from this model for about 54% of the variance in the data. So doing an okay job of predicting the likelihood of actually observing an emergency room visit in patients from our prediction model. And the other thing that we can do with the same data is then dump it into a program that R provides very nicely for us called random feature estimation or something like that. I've forgotten what the name of the program is at the moment. But it allows us to look at what are the variables in our data set that are actually accounting for the most important part of the prediction. And what we see in this case is that we have several variables that are very important, NCON, NPROC, NDRUG, and yeah. So now I'll explain what the variables that went into the model are. What we did was we took every patient and we counted simply for this patient how many different distinct diagnoses was this patient ever provided. How many distinct different drugs at the clinical drug level was this patient given? How many different procedures and so forth. So these are very global features, just counts of the numbers of these things that the patient was exposed to. The other thing that we did do in this, because some patients are in the system for a long time, some patients are in the system for a short time, is we fit a linear model of years of duration to the counts and corrected them for the amount of time the patient was in the system, so that we're now looking at a weighted estimate of the number of conditions and so forth. But we can see from that anyway that these very global variables are accounting for a lot of the variance in our data, and things like their type of insurance, was it public, private, or other, is also fairly important. Some of the things that fall down the line here are less important. The graph on the left, what it's doing really is telling us how frequently a variable like NPROC showed up as the very first split in the tree, or how frequently it showed up as the second split and so forth. So the depth in these graphs is how far down your tree you have to get before you decide that this is an important variable that I'm going to split on when you grow the classification of regression tree. So just summarizing what I said, the one thing that we wanted to do, because those were just these very global demographic features, we wanted to look and see whether if we included information about specific drugs that the children were given or specific conditions that they were diagnosed with, that would make a difference in the amount of accuracy of our prediction. To limit the number of different conditions and drugs we added to our data model, all we did was take the ones that occurred most frequently, and we took the ones that accounted for about 80% of the conditions or 80% of the drugs that were diagnosed as the mark off for each. So that left us with 749 condition features, that's different conditions that were diagnosed, and 150 different drug conditions. Ran another random forest analysis now with those added conditions, and what we see is that it ups the variance explained from mid-50s to around 60. So it provides a little bit of additional help, less than I had expected, frankly. And the importance measures from this larger analysis remain very much the same as they were before, though, with the number of procedures and the number of conditions and drugs being relatively high on the list. We now see that it is dragging in some drugs and some conditions. The D designation here is a drug concept. In fact, that drug concept is ibuprofen. And these two C concepts are conditions, and they are both seizure and epilepsy related conditions. So if the patient had either of these, the frequency with which those were designated in the electronic health records is partly driving the regression model in this case. Now, the analysis I just showed you is a little bit, it's not prediction really, it's characterization, if you will. We're mining the data to find out what are the relationships among the variables here. But I would never try to use a model like we built with the regression trees to predict the future of these patients, because it was just not designed to do that and not calibrated to ever unseen data. So the other thing that we tried to do was then classify the patients as those who would or would not have a visit within a given year. Because we had 3 years of data on all of the patients, we could use the first 2 years of data from the patient as the history, and then look to see whether or not they had an ED visit in that 3rd year, and that would be the quantity that we're trying to predict with it.
Is that any ED visit or an epilepsy-related ED visit?
Good question. In this case, it is actually any ED visit, so it's a little noisier than it might otherwise be. Here we start again with just the analysis that includes sex, ethnicity, race, number of drugs, procedure conditions, number of visits overall, the type of insurance, how long they stayed in the emergency room in the past, the number of emergency room visits in the past, and when they were an inpatient, were they in the hospital for a long time or a short time, and the number of inpatient visits. And use that to try and then predict, based on 2 years of data for each child, are they going to show up in year 3 in the emergency room or not? And there we're now looking at, again, somewhat cheating, the out-of-box estimate from the random forest. We didn't, in this case, completely withhold a test set. Instead, we allowed random forests to tell us, for things that were not in the forest that was grown, how well it was doing. So we're getting a somewhat optimistic 21.9% error rate in classifying these patients. Looking at the receiver operating characteristic, it's 82 is considered pretty good. So it's actually doing a pretty good job of taking the out-of-box estimates. Moving quickly because I see time is getting fast. One of the things that we've been doing a lot lately is looking at deep neural network models that we can apply to the same sorts of analyses as random forests. So I very quickly ran some analyses using keras. RStudio now has a really nice TensorFlow and keras suite of applications that are sort of layered into RStudio so that you're able to use them pretty much right out of the box, with some fairly good examples for getting started. So we then do have to convert from the random forest, which used multi-feature columns. So in the random forest analysis, we have sex, which is either male or female, and random forest is happy with that designation of a single variable called sex. The DNN doesn't like to do that. Instead, we want to divide sex into 2 distinct categories, either male or female. And if you're female, the female gets a 1 and the male column gets a 0, or vice versa. So that's a one-hot designation, and we do that for anything that's a categorical feature in the original data set that we were using. So that takes that simplified data set with around 20 features and expands it to about 34 because we have to add columns for each of the levels of each of the features that we're working with before. And then we put it into a model that looks a little bit like this, where we have our 34 input features that are going into dense hidden layers, each with 64 nodes. And those are just RELU nodes. And then those go to just the two possible outputs, either yes or no for ED visit. And the outputs are scaled using the softmax scaling to give us values for both of those between 0 and 1, which is sort of a quasi-probability of it being A or B. And using that approach, this time we really did hold out completely a test set. It turned out this was just randomly selected. We have 50 patients in the test, or 360 patients, I'm sorry, in the test set that was not part of the analysis and training. And that included 50 kids who did have an ED visit and 310 kids who did not. We ran the analysis on the training set, which was all the other kids in the original data. And then after completing the test, tested it on the test set. And this is the results of doing that. Almost got to 80. The very rough-looking curve here is because there are so many fewer data points in our AUC for this group. Last point, we can then start to look at the variable importance from the DNN, this time by randomly assigning random values to a specific feature and seeing how that affects the outcome of the model. And that's called a permutation process. So based on that, I guess, not surprisingly, and maybe even as an encouraging point, the number of prior ED visits in the first 2 years is far and away the best predictor of the number of ED visits in the next year. After that, it appears that we're doing some profiling of our patient population. We do get down to the number of procedures, number of years, number of conditions, and so forth that are also still contributing to the prediction of the model. But it's a different way to look at this, and the other thing that we're moving towards with an analysis like this is to then be able to use recursive neural networks or long short-term memory units to try and look at that first 2 years and see, can we get some trajectory information out of those that would give us an even better prediction of the final part of the analysis. So right on time. To summarize, I hope you've all learned a little bit of something about PEDSnet that you didn't already know, and seen a little bit about what we're trying to do with those data for Nemours patients and ways that we hope to be able to use the data to improve patient care. Okay.
Hello.
I do want to also thank Dan, Chris, Dr. Lawless, Dr. Piat, Dr. Jane, Dr. Malik Chavelli for all of their input in helping us to decide what things to look at in epilepsy patients and funding and driving the work that we're doing.
Thank you so much. Any question? Is there a question on?
Yes, hi. Can you guys hear me? Sorry, I'm
Yes.
calling from offsite. Yes, hi. This is Dr. Jane here, and thank you for the presentation. Obviously, I still learned a lot more than what I thought I knew. Just a couple of things. There was one question raised about the vitamin B6 that figured, because we use that often in conjunction with keras because it may help mitigate some of the side effects of the medication. Hence, you see vitamin B6, prominently featured as one of the concepts, I guess it's called. One question that I had earlier, even when we were communicating about this topic, is about, is there a fear that, like you said in your last slide about profiling ED visit, now obviously we have a different intention, but could it be misused by insurance company at some point? And, because obviously it's about economics also eventually, although we are more concerned about health.
I think that's a really good question. I don't think I'm qualified to answer it, but I think there's a good reason to be concerned about how some of these data would be interpreted by different people who have different objectives in mind than necessarily the well-being of patients.
Well, I think that it's used currently actually by health insurance to determine to do more of a case management process where in order for them to decrease the number of ED visits and to improve the care of their patients, I mean, they try to determine who are the patients who are at higher risk of ED visits, and then do proactive in protecting or in caring better, or putting together intense case management process. Mm-hmm. I think that's another way to see it, not so much as denying insurance to these patients, but more to improve their care. Mm-hmm.
Yeah, I have a question. So you mentioned, which I thought was really interesting, using the concepts in a term document frequency type of matrix. Have you guys played around with maybe using that data, like encoding that as like an embedding matrix, the word to vec type of thing as an input?
Yeah, that's when you get those 14,000 features in a row. That's one of the sort of standard procedures really for reducing the dimensionality of that is you can actually calculate skip grams on that and look for patterns in the among the 14,000 concepts to find a smaller dimensionality, a solution to the problem that still captures most of the variance. So yes, we have. I haven't figured out how to work the embedding correctly in keras yet, but when we do, that's certainly something that we do. Good point.
I'd love to hear about that.
This is more of a translational clinical question, so I don't know if this is outside the scope of what you were focusing on. But so now you've got you can predict patients pretty well. Is there any thought to what kind of clinical interventions might work? So with your neurology colleagues, do they suspect a lot of these cases are medication refractory epilepsy, or are these patients who, for whatever reason, can't take their medications consistently, and so maybe that would suggest a different type of intervention? Are these the types of conversations that are being had?
I think those are the kinds of conversations that should be had.
Yeah.
One of the things that we can't do with PEDSnet, because it contains only the discrete data, we can't dive into the notes fields and see if there's work comment there related to non-compliance with the medication. We get maybe somewhat of a proxy for that with a combination of the insurance and the number of visits. With public insurance and relatively few visits that aren't emergency room visits, maybe that's telling us something. Maybe in that case, more contact with the patient would be the remedy. Just reaching out, finding out, do you have a problem getting here? What can we do to help you?
This is a very wonderful presentation. I learned a lot from your talk. Thank you very much. Yeah, I would like to know, for the model, when in your data set, I think the foundation is to build up a very good data from the different resources. So I think if you look at the number of traces, if you by using the forest, random forest, if you just use 5 features, you can get the account for the variation about 56%. And then you increase it a lot, the feature from 5 to 1,500, just increase about 4 more %. Yeah, so in that case, if we, in terms of feature selection, possibility things, so it seems like we do not need to increase from 5 to 1,500.
I think that's a really important point. It is one of the things that we think about a lot when we see something like that. I was wondering if I wouldn't see a much larger impact of adding the additional, what was it, 1,000 features or something, 8,000, I forget now. Whatever it was, we thought by adding these additional features, we were going to be getting a nice increase in the prediction. We didn't, which of course first means that just from those demographic and sort of medical complexity, maybe the number of conditions you have is how complex a case you are. To the extent that it's a proxy for complexity, maybe that's where 90% of the variance comes from to start with. And there's just not that much more to be learned from whether you have this type of epilepsy or that type of epilepsy or something.
I think maybe the two possibilities is that maybe before run the analysis, we can check two things. One is check zero variance or near zero variance. That could be bound the number of features.
Oh, yes.
And the second, maybe we can check the collinearities for this very huge features so that we can significantly maybe reduce the collinearities and then combine this zero variance, near zero variance, and the collinearities, and then that could improve the probability.
It could. Certainly, one of the things that I didn't try to do with this data set, one of the things that is commonly done is after you've run that first analysis, you look at what are the variables that are accounting for nothing in this, and I can throw them out, and then I'll rerun it with a subset of the variables. And you keep doing that until you actually find that you're starting to make your fit worse, and then you can stop. The nice thing about random forests, unlike, say, a standard regression analysis, is that the collinearity isn't necessarily hurting you a lot. But there certainly is tons of collinearity in the data that we were using.
Thank you.
Thank you, Tim. That was great. We know that matching or putting the data into OMOP is a huge amount of work. We've tried. So how much time, do you have all the EPIC data into the OMOP model now?
Yes.
Wow, that's really super impressive. And how much time did it take you and your team to do that?
Let's see, we started in 2014.
So it's
an ongoing process.
It's still an ongoing process.
It never ends. As anyone who's worked with this sort of data knows, there's always something you can discover after the fact that, I should have done this, or you have, like, for trying to decide what condition code to assign to a patient. Well, the first thing you look at is the primary diagnosis, and if you don't see anything interesting there, like that field is null, then you look for the secondary diagnosis, and if nothing is good there, then you look in the problem list, and if nothing is good in the problem list, then you look at the billing. And so you go through this hierarchy of things to check until you maybe find something, or maybe you don't, and you end up with a zero concept there. And then later on you discover, well, there's this other table that I didn't know about among the 12,000 tables in EPIC that if I had looked there, I'd have gotten the right answer.
And so do all the investigators now at Nemours have access to, they can do queries directly into OMOP themselves?
With Atlas.
With Atlas.
We don't literally give everybody patient level access to the data. That we're still requiring that if you need to get patient level data, you submit to the IRB, describe what you're doing, and it'll either be declared not human subjects research if there's literally no PHI in what you want. And we can get turnarounds from our IRB in as short as a couple of days sometimes. They only review them, I guess, periodically. So if you wait until just before they're ready to review, you get a response back the next day. But then if you're asking for actual dates or zip codes or something like that, they'll declare that it's an exempt. But
so then your team is doing the data extraction and building the data set when they are PHI?
Correct. Correct. We have a couple of analysts now whose job really is to respond to, remember in the slide that I showed you of our internal website, there's a request form. If somebody submits a request form there, one of our analysts will take that request and run the model or build the query, which is typically an iterative process, as you know. Even with a much simplified data set, it takes a while for the analyst and the investigator converge on what they mean.
So how many, did you start in 2014, this data goes back to 2014, or?
Oh, the data in our data set goes back to 2002.
And you have provider information?
I think.
Provider information, you do.
Oh, collaboration. Any other questions for Tim? Thank you so much again.
Let's just